Today we have Itai Ashlagi here from MIT. He's been working on matching markets and was a postdoc with Al Roth at Harvard and is now at Sloan, and he's going to talk to us about stability in large matching markets with complementarities.
Okay, thank you for inviting me. So this is the topic of the talk. It's matching markets with, and I will deal with complementarities issues. But the focus really will be matching markets with couples. So there's we know a lot about when there's both sides are singles, or one side is like hospitals or something like that, and the other side is singles. But when you're married couples and looking for two jobs, things become more complicated. So, and the motivation from this work is really the market for matching residents, medical residents to hospitals. So just a quick background on this market from numbers from the last year. So over 16,000 graduates from medical schools in the US, over 23,000 residency spots, so there's more slots than doctors. The extra access is filled with foreign doctors and so on. So actually there's more than 23,000 doctors, but think about it, there's much higher priority to US doctors in this market. So these numbers are going to motivate our model. So in a match, there's in two-sided matching here, we'll focus on one side. There's like medical programs or hospitals. They have preference lists over the doctors themselves. Here we have Alice, Bob, and Charlie, and Alice, Bob, and Charlie have preference lists over the medical programs. Okay, and you don't have to list everybody. Usually, those doctors list who they interview with, and so the same for the hospitals. They submit the preference list to the match, and the match outputs assignment. Okay, who's matched with, according to some algorithm. Okay, and here how it looks on match day, and some people, and most people are actually happy. Not everybody's happy, and an important property that we already know is important for those matching markets is stability. So stability means that if you get your third option, the first and second option you can't get them. This hospital once got someone they like better than you. Okay, so for example here, Bob and Charlie. This is a stable matching, and you can see this easily because every program here got his best preference. Okay, so this is a stable match. No hospital and program can deviate from their match and go together and both be better. Okay, so this is a stable match. And in fact, the NRMP, the National Residency Matching Program, used something very similar to the Gale-Shapley algorithm, which is used to find the stable matching when it's a world only with single doctors. So the matching algorithm they're using is a doctor proposing version. The algorithm is called deferred acceptance, and there are two versions: doctor proposing and job proposing. But they're using the doctor proposing deferred acceptance algorithm. Basically, it goes as follows: every applicant on the list, every doctor applies to his best first on the list. Every program rejects everyone except the top preference that applied to it, and then you go on and apply to the next one on your list, and so on. And the programs always keep the best offer they got. And this obviously terminates. Everyone has just one list, and it terminates in a stable match. It's a very simple exercise to show it. So this has been used for a long time, and it has very nice property. One is, of course, the stability. Okay, but other two nice properties is that it's safe for applicants to report the true preferences. It's not necessarily safe for doctors to, for programs to report truthfully. Another nice property is that every doctor will get the best stable matching among the set of stable matching. Okay, so the set of stable matching is actually reduces is the lattice, and you get the doctors get one side of the lattice, the best for them. So over the years, actually, lots of in the beginning, when medical studies, there were not too many women, but women more and more are studying, and couples have been starting to evolve, and actually there's lots of couples today, and they're getting married, and they want to work in similar places at least. So there's been one problem with the medical match, the algorithm. It didn't allow couples to express their preferences, and that caused a big decline of participation of people who are members of couples, doctors who are part of couples, participated in this match. And they were looking for jobs directly with hospitals and not through the match. And in those years, 1995, 98, Roth and Pearson designed a new algorithm that the main thing is to allow couples to express their joint preferences. And in 1999, it started to be adopted. Okay, so the main important thing is to allow. Here's a couple. They introduced allowing couples to express their preferences. So the couples can, in this algorithm today, they list pairs of hospitals or programs. So you can list the same one because you want A in New York A and New York X, and then you want maybe New York A and New York Y, and so on. Yes?
How the statistics that you showed, how many percent of the doctors are married to each other?
How many?
What's the percentage of the doctors?
So how many couples? So
yeah.
it's about 5% of the doctors today are couples. So between 9 to 10% of the doctors are partners. So this is how you can list today the preferences, and they designed an algorithm for it. The algorithm is not, it's described in one of the papers, but it's haven't ever been analyzed. So here's what you just asked, the percentage of couples that has been growing over the year. Today it's about 800 couples, over 16,000 doctors. So one thing that couples introduce is complementarities, because if maybe we want two jobs and not just one job. Right? My preference depends on your preference and vice versa. So already in 94, Roth and Klaus and Klein provided even a simpler example for instability in this study. So I'll show you the Klaus-Klein example. It's a very simple example. It's just one couple, one doctor, and two programs. And you will see here that there's no stable matching. So here, Alice and Bob are a couple, and they're listing jobs 1 and 2. After that, they don't accept anything. Again, you don't have to list everything. And these are the preferences of the program. So if the couple is assigned to 1 and 2, then you can see that Charlie and Bob, and Charlie and the program number 2 are going to be a blocking pair. So program 2 is willing to accept Charlie over Bob. So if Charlie is here, Charlie prefers to go now to program 1 because program 1 is empty and is willing to accept him. So Charlie and 1 are a blocking pair, but now Alice and Bob will be accepted again to 1 and 2, and Charlie will get out. Okay, so this is a very simple example, probably the most simple example that you can come up with. And but one thing you see in data, at least assuming that the data is true preferences, is that in the last 12 years, a stable matching has been found every year. And there's other markets that their algorithm is used, and also stable matching has been found. So at least if the data is true preferences, then it's a stable matching according to the data. Okay, has been found. And actually Roth, Kojima, and Patak started to study this question, what's going on here. And they looked at the large market approach, and we're going to look at a similar large market, and I'll mention the results in the next slide, but let's start with the model here. So we have n doctors, and we have k couples where n to the 1 minus epsilon couples. So the couples are growing in a sublinear rate. There's an excess number of residency slots, and lambda is a constant here. And there's up to C slots in every hospital. And C also is a constant. Okay? Now, doctors and couples have random preferences over hospitals, and hospitals might have any preferences over doctors. So the randomization is on the doctors. Okay, now when I'm saying random preferences, think about everyone. If you're a part of a couple, every member of the couple is forming his own list randomly. And then you're joining these lists either in the more natural way, or by some aggregating function that takes whoever appears on my list. In the joint preference list now, if I put someone on my list, so I'm working down those hospitals A, B, C, D, and this one is ranking D, A, E, F. So in the joint list, if I put here A has to appear here. If this is A, B now, then A has to appear here and B has to appear here. But B doesn't appear here, so it can't be here. So F can be here, for example. So this is a valid aggregation. A and F is a couple is a pair in the list, and it's feasible because A appears in this list and F appears in this list. Okay, and
when you say random preferences, is it uniformly random?
So it's almost uniform. So no, when I'm randomizing for each one of those members of the couple, I'm not allowing any hospital to be infinitely better than some other hospital. So it's unbounded by.
But in reality, there's only some hospitals which are much more valued over other hospitals in the U.S.
So that's right. So first of all, this is a first approach, but you can think of this as now thinking about the large markets in New York area or things like that. Okay, given that you're focusing on those big two metropolitans.
And also, like, I'm happy to appear. Like A and F aren't a pair in the list. So basically the list of pairs is all crosswise pairs of the two.
So the aggregation doesn't have to be all the possible pairs. So aggregation can be, I'm randomizing for each member of each doctor, and now aggregation can list any number of pairs, but all it has to satisfy is that if someone appears on this side, he has to appear here. So first I'm randomizing a list, and that's it. But
in what order do these pairs appear?
What?
In which order are the pairs in the couples list?
So here, in this over here?
Yeah.
So here it can be in any order. So I can have A and then B and then again A. So this is a valid list. But all I'm requiring that if I list here someone, he has to be on that side. This is first I'm randomizing this, and this is not a randomization now. This is any aggregating. Now, this is valid. It's valid when the preference lists are short. That means of constant length. And the reason for and the motivation for that for the short preference list is that you only interview with a finite number of programs over 2 months or something. You're applying to interview and so on. If preference lists are long, we can't use this aggregating function. We're just randomizing for each member of the couple almost independently, and what will happen, and this will be the joint list. Okay, so if lists can be of length of n, then we're not allowed to use this aggregation function. This is just the list we're coming up. Okay. So there's some fitness scores, but again, it's close to uniform. Think about it like that. So, here's what we're showing. In a large market, when n grows to when n grows, the stable matching exists with high probability. So, and we propose an algorithm that I'll show very soon. It's called sorted deferred acceptance that finds this finds such a stable matching. In addition, nice properties from the only singles market holds. Like one is that doctors, sorry, that doesn't hold with the single markets, but in large markets it's been shown by Patak and Kojima that the hospital sides are not willing to manipulate when the market grows. Also, Nicole and Muhammad Madian showed this in one-to-one matching markets. Then what will hold here is that every side will be better off just reporting truthfully. And that will be a approximated best matching when the market is large. Another nice property is that almost all doctors, every doctor with ex ante will get with high probability the best stable match. Okay, but I think the main result here is the stability that we get when the market grows. Okay. Now, Kojima, Patak, and Roth, what they showed is that. So this is screwed up a bit. If the size of the number of couples is less than square root n, strictly less, so n to the half minus epsilon, then you'll get a stable match. Okay, so our improvement here is really from this half less than square root n to any any 1 minus epsilon. Okay, and I'll explain why this is not just a cosmetic result. This is a serious qualitative result. Okay, so there's a big difference what we're doing than what they're doing here. I think so we'll get to that. Okay, so it turns out that this result is tight. So if the number of couples are growing in a linear way, then you have with constant probability no stable match. So no algorithm will find anything. Okay, so here we have two different types of results. If the preference lists are long, or if the preference lists are short. So if they are long, we need a large excess for the proof. So there exists some large excess of hospitals that you get this result. And we think that for any lambda larger or equal than 1. And if the preference lists are short, you essentially get this large excess for free in the proof, and you don't really need it. And that's why for any excess, you get that this result holds. So there's no stable matching with constant probability. So I'll talk about both of these results. But let's start with the positive side. So we're in the sublinear world. Couples are not growing sublinearly. Okay. So what we would like to do is run the deferred acceptance only for singles. Here's an idea. So start with only the singles, find the stable matching only in this market, and then start adding the couples. Let them start in apply, just in a similar fashion as in Gale-Shafi. You start applying, maybe they called some other single doctor to leave their job, he keeps on applying and so on, and maybe in some point the doctor for the couple is rejected, so the couple has to keep applying and so on. So we'll start with the singles, and when we'll try to find an order of the couples so that they apply, and eventually if no couples is going to be evicted in this process, we're going to end up with a stable match. Okay. So if we do this kind of idea, we'll obviously run into problems because we know we have examples that fail. Okay, but what fails here is exactly what we did before. So the single. This is the idea that we came up with. So start with a single, find a stable match. It goes directly to program 1. But now, by letting the couple apply, of course they're a blocking pair, and Charlie is rejected. Okay? So it doesn't really work, but what happened here is kind of, and now Charlie can come back and is a blocking pair and so on. Okay? But this idea doesn't work because of these kind of examples. But what we're looking for, if we can do this for some order, so in this is a very pathological example, we can't solve this. But if in a large market, the idea will be to find some order of the couples such these kind of things don't happen. Okay, we'll find a stable match with singles, and then start letting couples apply, and hopefully with some order this will work. Okay, so we introduce a notion of influence graph, and the idea is that in this graph, couples are going to be nodes, and the couple there's going to be an edge from one couple to the other if, when he applies, he causes this other couple to be evicted through some rejection chain. Okay, so it may be evicted some other single who evicted this other couple. So in here, what happened with our example is that when Charlie was inside, Alice and Bob applied, they evicted Charlie, who evicted again Bob. Okay, so this couple is evicted as a whole. If Bob is evicted, the whole couple is evicted. So the couples graph is going to look like this. The node, there's only one node, there's the couple, and there's going to be an edge from the couple to itself. Okay, because there's a chain through Charlie that causes the couple to be evicted. So imagine you already have a stable match only with singles, and now you put the couples in. So if A and B is a couple and it applies, it causes this rejection chain, and it evicts maybe this other couple, and this couple is causing to evict this couple by this rejection chain through G. So in this case, the couple graph is going to look like this, because there's each couple is influencing another couple. It's causing some other couple to be evicted. And this is something we want to eliminate, exactly those cycles.
Is the couples graph independent of the order of insertions of couples?
It will be independent. We're going to construct it independent. Yes. We're going to do these edges. We're going to write down these edges with hypermobility. That's going to be that. So it's very hard to keep track. If you start constructing this dependently, it's almost impossible to keep track on how the graph looks like. So we're just going to these edges are going to be edges with hypermobility. So here's a different couples graph, and this is something we want. We don't want cycles. In this graph, the graph looks like this, and this graph is good because we want to. In this case, we'll just insert AB before EF, because EF will never evict AB. Okay, so the sort of deferred acceptance algorithm is going to look for an insertion order such that no couple is ever going, no couple that applied before some other couple will be evicted by this other couple. Okay, so nobody evicts couples once you start applying. And what we want to show is that this eventually the proof will be to show that this couples graph is acyclic with hypermobility. So if this is the graph, you can insert, there's two orders of insertions. You can put A, B, C, D, E, F, G, H, or you can put it in this order. So basically, you're looking for a topological sorting of the graph. Okay. So the algorithm is the following. We're first looking for just deferred acceptance only with the singles market, and then we're starting with some order pi. We're starting letting couples apply, and again, once you apply, if some doctor is rejected, he continues just as similar fashion as Gail Shapley. It doesn't matter if this doctor is part of a couple. If it's a part of a couple, all the couple continues, and so on. But what we do here is, if A, B evicts C, D, this couple evicts this other couple, we're going to put A, B ahead of C, D and run again the algorithm. Okay, so the heuristic here is that A, B cannot be after C, D if he evicts it. Okay, if there's a chain, if once they're doing this application process, he evicts C, D, I'm going to change this order such that A, B applies before C. Okay, if we end with no evictions, that's great. If we come back to the same order, for example, we fail, or if the couples graph contains a cycle. Okay, so the idea will be to show that the graph is acyclic, and high-level lemmas, I won't get into them, but with high probability, a couple is going to pick some other couple with probability 1 over n, approximately 1 over n. With probability going to 1, the couple graph is acyclic. Okay? Now, I want to say now something about Kojima, Roth, and Patak's results. So, if you look at in the idea of this influence graph, or the couples graph, what they showed is that if the number of couples is less than square root n, and then you have a graph with these number of couples, and if each couple is evicting some other couple with probability 1 over n, this graph is going to be empty with high probability, whereas n grows, right? So basically what they showed that as long as this is the number of couples, not more than this, no couple is going to evict any other couple with high probability. Okay, and this we see this in data that it's correlated. You don't expect that in the entire market, just because nobody's going to evict anybody else. Some order, the order does sometimes matter, and maybe because you were lucky, you applied before me to some other hospital, and you were just ahead of me, but that hospital wants me, so I'm going to evict you. Okay, so this is essentially the result. So what we're going to show is that with n to the 1 minus epsilon couples, this graph is acyclic. And with any number above square root n, this graph is definitely not empty. Okay. So how we're going to construct those graphs is the following. So we're starting with what's called an influence tree for a couple when this couple is the only couple in the market. So suppose we found now a stable matching only with singles, and now this couple is going to start applying. And I want to see who are the doctors in hospital that this couple, by applying, is going to influence. So who is he going to help? Who are those doctors that are going to be rejected because of him, and who are those hospitals that are going to be get more applications because of him, and so on. Okay, so we're going to define this by pairs of hospitals and doctors. Okay, so a doctor and a hospital are going to be a pair in this influence tree. If by applying I cause this doctor to go into hospital H. Okay, so this is the influence tree, and and now I want to start drawing edges between different couples. So suppose these are two couples, and what is written here is that in this picture here, if this is a couple that causes a rejection chain that eventually causes Dr. D prime to go to H. Now remember, this couple doesn't exist. I'm building now the graph only for one couple in the market. So suppose so this D prime and H belong to the influence tree of Ci. Similarly, so for Cj. So similarly for Ci, if he causes this rejection chain that causes D to go to H, then DH is in this influence tree. Okay, but now H prefers D on D prime, so this gives motivation, at least, or the idea that we want to have an edge from Ci to Cj. We want Ci to apply before Cj, because if Ci applies first, this couple might come. If Cj applies first, this couple might come, and this doctor will be evicted because of it. Okay, think about D and D prime can be part of the members of the couple also. Okay, so whoever H prefers gives rise where I want, in what direction I want to put the edge. Okay, so again, every influence tree is now if only the couple is defined is the only one in the market, and now I'm just defining the graph in this case. But now the real world is that there might be other couples in the market, and so for this we don't keep the order. We just we're going to simulate adversarial rejections. So when I'm applying, and I'm causing a rejection chain. On this rejection chain that I'm causing, I'm going to simulate adversarial rejection that maybe have been caused by other couples that applied before. Okay, so I'm going to. These chains can be much more complicated. It can be trees, and then maybe this D prime cannot come to H because some other couple was causing some other doctor to come here, and this D prime has to go somewhere else, and so on. So I'm going to construct it with some R, and R is going to be the number of adversarial rejections. Okay, so this is the idea to go from a dynamic world to a static world. And now we're going to show that the couples graph that is constructed from this notion is going to be acyclic with high probability. Okay, so from here, what you need to show, I won't show it, but I'll say just the high level results. You want to pick some number of adversarial that is catching reality with high probability. That if you are, that if you are going to be rejected in reality, you're going to also be belonging to this influence tree with high probability. And then we show that the couples graph is acyclic. So this is a very important lemma to show that this number of adversarial rejections that we choose is conservative enough to capture what's going in practice. Okay. So this is a positive result. And now what happens with when the number of couples grow in a linear way? So the idea here is going to be, so here the result is stated for when preference lists are long of any length, not constant. And what we're going to show here is that you can find a submarket, a small submarket, so if nobody else exists, there's not going to be a stable matching in this small market. So basically we're finding something very similar to the counter example we showed. If this is the hospitals, and these are the doctors. So there exists some with constant probability. There exists some market that if you throw now everybody else, there's no stable matching. And now you throw the rest of the doctors out. These are the doctors. These are the programs. So if now there exists some submarket that if I ignore the other doctors, there's not going to be a stable matching. And now with constant probability, none of these doctors are going to ever apply to these hospitals. Okay, and that will induce the result. And we need here for the proof, we need here a large excess number of hospitals. Now you can see that if preference lists are short, none of these hospitals, you don't need this lambda larger than 1, and lambda can be larger or equal than 1, because none of those hospital doctors is ever going to apply here at all. It's not going to rank them on the list with constant probability. So we don't know to prove this for long preference lists for larger lambda, any lambda larger equal than 1, but we believe it is true. Okay. So we did some simulations from a market for psychology interns, and now this market is not big. It has it's almost impossible to get my data from the NRNP market. We have here about 3,000 doctors and 20 couples, and the years are 1999 to 2007. And SODA was successful. That's a lie. It's not all of them except from 1 year. Every year there was a stable matching that we found. We had to alternate SODA a little bit in order to find in every year. So 1 year it didn't. So in 1 year, so that as it is, didn't find a stable outcome, we had to change something small to find. I'll mention what it is. So there's not many couples here, but we did other simulations by taking those doctors here in the market and merging them into like synthetic couples according to their geographical origins that are listed. So, and we went up to 160 couples and we got really nice results. Almost all of them had stable outcomes. Here's these couples graphs in the markets. In those years, the couples graph was empty. In these years that we had some edges. Now it's not too dense because the number of couples is very small, but there are edges in those markets. And in fact, these couples graph can predict very well what's the probability that you'll find a stable matching if you just choose randomly some order of the couples to apply after you find a stable matching in the J shot without them. So, for example, if I just random some order, I expect here in this graph, for example, to find a stable matching with probability half. Okay, if I by accident choose 19 to apply before 3. Okay, so these couples graphs at least somewhat give a really good understanding of what's going on, and they predict very well these orderings. Okay, so you can imagine an algorithm that you just find a stable matching only with the single markets and just draw an order of couples to apply and start again and random again and again until you find one. But if there's going to be lots of couples, those graphs are going to be very dense, and that's going to be very hard to find, to be lucky and find one. And that's why SODA is, that's what we show with the 160 couples, that those graphs are very dense, but still SODA works very nice. So it works fast to find this order. Okay. Yes.
What's the significance of the couple displacing itself?
Okay. So this is a serious issue. This is just the example that we saw in the counterexample that we saw. And here, there was eventually a stable matching in this year, and what we did is something that both parents are doing. So instead of going back to trying and applying back to the same guy, just go down the list and maybe somehow things will resolve. Don't go back to the same guy. Go down the list and maybe something will resolve. And it happened here. So that's an interesting issue. Why is this happening after all? So it wasn't just something small that they did there. It's a question. But there was a...
Also, the couples graph could depend on the stable matching you pick for the single people, right? So...
Yes, so we
build
build it
if you get a bad cycle like that, you can rerun the single,
so you can...
change the singles.
Yeah, you can let them... they don't necessarily have to be in the best
Around in the lattice,
single one. Yeah, you can do that. And we also, we also find the singles first, and maybe some other algorithm will work. Yeah. So there's lots of other possibilities. It's interesting, to understand why there's still lots of. That's an intuition why there's lots of more possibilities. Okay, so we did other simulations and another conjecture, just on according to our model and not to data. And we see here that as long as the linear coefficient, if the market is growing linearly, as a function of the linear coefficient, the success probability is growing. And this is something we don't know how to prove, but it's interesting. It's an interesting observation. In fact, we think if the market grows, it will converge to a constant that depends on this linear coefficient. Okay. Although we have some jumps here, but it's still. And you see here for the 5% of the couples here, the success probability is pretty high. But again, it's something interesting for future. As the number of couples or fraction of them is growing and growing, it's still interesting to look for either to understand the differences, for example, between our algorithm and the Roth-Pearson algorithm, or to come up with other algorithms, or even different models for defining, for example, looking at more geographical preferences in these markets. So to summarize, a stable match, what we do is find a stable match as long as the number of couples grows in a near linear rate, and it's tight as long as if it's linear, the number of there's no stable match with constant probability. And the algorithm, so finding also is a big issue. Often we know that with couples, for example, even determining if a stable matching exists is NP hard. But here we come up with an algorithm that finds one with the high probability. It's interesting, again, to compare our algorithm to the Roth-Pearson algorithm. So I think qualitatively, eventually it will lead to the same result. It cannot lead to much better results because we know our negative result. But what are the little differences that might happen there between those two mechanisms? And I think the tool of influence graphs, couples graph, is interesting in other markets, such as with complementarities. It's something we're looking now at markets with money. In auction situations, for example, if there's not too many complementarities, we'll get, for example, a valuation equilibrium or things like that.
Questions?
Do these results depend on the independence of the preferences when you're randomizing? Is that
So
if you introduce the slightest amount of correlation, then you wouldn't have the same existence or non-existence?
So it depends, but I don't know that.
The reason I'm asking is because you made the justifications for the short preference lists was that hospitals only interview a small number of the doctors, but that's kind of endogenous. Right? Like as far as which doctors they end up interviewing might be correlated with what the doctor's preferences are. So it's not a complete argument to justify looking only at the top.
So even in a model that every side has a complete or everybody agrees on who are the best doctors, what's the ranking of the doctors, what's the ranking of the hospital, and maybe there's some epsilon in what we want. Even in that model, we're not sure. So
okay.
It's really, yeah. I don't know, maybe things work, but I don't know.
Okay.
Okay.